So today we are doing section 9.7 and section 9.8, which is molecular orbitals and bonding. So this is a unit that isn't really covered that much because it's a lot more difficult than the other units for the AP test, but it's still important information and should help you to understand the rest of the units as well. All right, starting off with some clarification. We're going to talk about the difference between molecular orbitals and atomic orbitals. So atomic orbitals we've been previously working with the electron configurations and the shape of the orbitals and stuff like that. And they represent the electron density in a space associated with a particular atom. So just that one atom, depict the location where the electron can probably be found in that atom. And that's our SPDF orbitals that we've talked about previously. Now, molecular orbitals are associated with entire molecules, and the electron density is spread out over more than one atom. It's spread out over the molecule. And in this unit, we call that delocalization. And so it again describes that most probable location, but throughout the entire molecule as a whole. And those are named with your hybridizations like sp2, sp3, all that stuff from previously in chapter 9. So this is just an example of how we have the atomic orbitals here and the molecular orbitals, and just the difference between how they bond and how they're shared in the diagrams. And it just kind of gives you a little more information over the molecules to show how the bonds are. So for this, we use our molecular orbital theory, and it describes our electrons in molecules by using molecular orbitals. So it gives us a good idea about the strength of the covalent bonds between those molecules, and our atomic orbitals are replaced by our molecular orbitals in the diagram. So like in this one, we're just completely replacing it to make our models. And this is just another example of some of the hybridization here and how that works out. All right, so coming back to our molecular orbital diagram. So this is the diagram that shows the interaction between the orbitals, the interaction between the two separate atoms, and shows the whole, obviously, molecular orbital. So to understand these models, we need to know two things: bonding molecular orbitals and anti-bonding molecular orbitals. So bonding molecular orbitals concentrate the electron density and hold the atoms together. And these are a lower energy state than the anti-bonding, which have very little electron density and have higher energy. It's a little bit confusing to understand, but once we get into drawing the models, it'll be a lot more straightforward. With that model comes our bond order equation, which is 1/2 times the bonding order electrons minus the anti-bonding electrons. So we're going to count the electrons within each orbital and put them into that equation, and it should give us an answer about how strong the covalent bond is. Okay, so for our first practice model, we need to again know that bond order gives an idea of the stability of the covalent bond. Okay, so we're going to start off with oxygen. Now, you don't necessarily need this, but I think it helps to have the electron configuration because you're taking two atomic orbitals and putting them together. So if you have this configuration right here, it helps with the process, but again, it's a very simple configuration, so not everybody needs this. So getting into our model, you see we have our two atomic orbitals here, atomic orbital, and that is just that exact configuration, 1s2, 2s2, 2p4, right? And again, we're finding the bonding strength between those two atoms because it's an O2. So what we're going to do is we're going to take these, and all of these sigmas are going to be first, right? Because sigma bonds come before pi bonds. And also, all these ones like this one, these two, these three actually, are all going to come before the stars. These are our bonding orbitals, bonding orbital, bonding orbital. And we fill the bonding orbitals of each level before we fill the anti-bonding orbitals. So obviously here we have 4 electrons to work with, so we're just going to go ahead and fill this in. We have our first 2 for the bonding orbital, and then the next 2 going to the anti-bonding. Now I'm going to keep these color-coded so we can keep track, because this at the end is going to go into our equation. So then, for this next level, I'm going to go ahead and get those 2, and then we're going to go ahead and get those 2 anti-bonding ones. Perfect. And now this one, we're going to go through again. We're going to go sigma first, and then we're going to go into our pi bonds. And then let's see, we have 1, 2, 3, 4, 5, 6. And over here we have 4, and over here we have 4. So we have 2 more. So those are going to go into our anti-bonding orbitals. So now this is where we are going to be using our bonding orbital, our bond order equation. which was 1/2 times the bonding orbitals minus the antibonding. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonding, and 1, 2, 3, 4, 5, 6 antibonding. So putting that equation right here is going to give us 2, which means that there's a double bond between the two oxygens. Now we can do this for any covalent molecule, and we will get an answer about how many bonds there are between. So we're going to go ahead and we're going to try an additional example. So find the bond between the N2 molecule using a molecular orbital diagram. You just set this one up just like the last one, and pause the video so you can work through it and come back whenever you're ready. All right, so starting off with this one, we're going to do the same thing. Again, I think it's beneficial to have this here. You know this configuration. And we're going to go back to our model again. Only this time there's 3 here instead of 4, obviously, because it's a completely different atom. And we're going to run through this one faster because we know what's going on. So we're going to go ahead and we're going to get through our bonding, antibonding, bonding, antibonding, all of our bonding. Right. And this time we have no antibonding because we only have 3. We fill all of these first. So 10 minus 4, once again using our equation, is going to get us 3, which, you know what that means. There is a triple bond between the 2 nitrogens. It's pretty simple. There's a lot that goes into it, but really, all these little parts, just filling in the boxes, it's not too complicated once you understand what you have to do and in what order and what all of your variables mean. It's really not that difficult, but hopefully this cleared that part up. So moving on to our next part, which is 9.8. So there's really not much to cover in this part of the chapter. I mean, all we really covered was paramagnetism and diamagnetism, so I'm just going to go over that. Paramagnetic things are molecules with 1 or more unpaired electrons, and they are attracted to magnetic fields. So this is an example right here. Our 2 previous molecules, oxygen and nitrogen, would both be paramagnetic because they have those empty shells right here, right? They don't have that full shell. So those would be examples of paramagnetic molecules, and I have some other examples down here. So diamagnetic are just the opposite, molecules with no unpaired electrons, and they are weakly repelled by magnetic fields. So here we are. We have every shell is full, and so here's some examples, right? It's pretty easy to understand. You have unpaired electrons, paramagnetic, or paired diamagnetic. That's all I have for today, and I hope you guys learned something.